Hi. 2 years ago I gave a talk on how to use RenderDoc to debug your driver. This time around I'm going lower level and want to talk about the tooling I made for Turnip driver, which help us debug various issues. I believe that most of it may be useful for other drivers as well. In addition, I will give a short overview of other tooling which helps accomplish similar goals, but for other drivers. But before, briefly about me. I took a part in developing 2 mobile games, and while I did not work much on rendering back then, I still saw quite a bit of fun driver issues. Afterwards, I accidentally started working on Mesa and debugged all kinds of issues in various games and applications since then. Now I've been working with Igalia for 3 years, and presently in the process of upbringing the new Adreno GPU generation in Turnip. Let's start by stating the problem. After you debugged a nasty GPU issue, half of the times you think, what if I was able to quickly edit the GPU packet? Or what if I was able to dump this buffer's memory here? Or it would have been nice to print that shader register. And every time you think, I will implement it later, and then forget about it until the next nasty bug. Last time though, it was not just a bug needed to be fixed, but a new generation of GPUs needed to be supported in the near future. Maybe you know that there is no documentation for Adreno GPUs, and all the information is reverse engineered. So there is a lot of what does this bit do kind of testing. This finally tipped the scales and the tooling was implemented. Though afterwards I believe that it is worthy regardless of having the GPU documentation. For now, I will talk about the tooling I implemented in Turnip. Just keep in mind that I may omit or miss some edge cases, since the point of it is to ease the debugging process in the common cases. Afterwards, I will talk about what other drivers have. Now, let's start from how we could improve the debugging of unrecoverable hangs. For recoverable hangs, there is, for example, graphics flight recorder, which uses breadcrumbs at API level and gives a probable range of calls where hang occurred. Or you just could go through draw calls and find the ones which hangs. With unrecoverable hangs, you have to reboot the system each time. In such case, graphics flight recorder is useless, and going through draw calls in RenderDoc is either not possible or too slow with all the reboots. And such unrecoverable hangs are not that rare occasion for us. The issue with graphics flight recorder is that it writes results to the disk, and what's written is far behind of what's happening on the GPU. One of the solutions would be to modify GFR to have synchronous mode, where GPU will not race ahead of the CPU and breadcrumb status would be sent over the network. Unfortunately, this would require at least one more Vulkan extension and more work on GFR. With another downside being that GFR works on API level, while in reality one Vulkan call may not strictly correspond to a single GPU command. In example, begin render path may internally use a lot of different 2D and 3D bleeds to clear and load attachments. What do we know about unrecoverable hangs that we should take into account? Luckily, at least from my experience, unrecoverable hangs are rarely caused by synchronization issues. So no matter how heavy-handed synchronization we would need, it likely will not affect the result. On the other hand, if we allow GPU to race ahead of the last known to the developer breadcrumb, even by a few commands, the usability would be drastically reduced. Another issue, even if we perfectly synchronize GPU execution with logging, some hangs happen asynchronously to the GPU packet that triggers them. Fun! A packet may submit some work to another GPU unit, and that unit may hang later on and bring down the whole GPU. It also could be impossible to properly wait for this unit to complete. So the current solution in Turnip is breadcrumbs are inserted after each GPU command, which has a chance to hang. GPU writes a breadcrumb and immediately waits for this value to be acknowledged on the CPU side. CPU in a busy loop checks the breadcrumb value. If new one is found, it is sent over the network. Only then the CPU acts the breadcrumb and GPU continues its execution. Here is a simple visualization of how it works. Surprisingly, it worked not as slow as I would have thought. Okay, what about asynchronous hangs I talked earlier? We have a simple way to deal with them. We require explicit input in TTY for each breadcrumb. Or we could add a configurable delay between them, which I probably should implement instead. Anyway, works well enough. Here is how it looks like in practice for Turnip. First we increase GPU hang timeout. Breadcrumbs could easily trip it. On another machine we receive the breadcrumbs via this nice script. Then we set where the breadcrumbs would be sent over the network, set the first breadcrumb to require explicit acts from TTY, kind of a breakpoint. Then we launch the workload and wait until the hang. Now that we have the last breadcrumb value, we reboot the testing machine and relaunch the workload with breakpoint just before the last breadcrumb. Then we manually act breadcrumbs until we have a hang. Here are the links to my blog post about breadcrumbs implementation in Turnip and merge request which implemented them, if anyone is interested. Now we will discuss what to do when you found something with breadcrumbs or when they are not helpful at all. Breadcrumbs are good for finding a command that hangs, but they cannot tell which part of the GPU state caused it, and they are useless for misrenderings. Some issues are not reproducible with breadcrumbs enabled or just have low reproducibility rate. Let's address the reproducibility rate first. For reproducibility, a simple solution is to be able to capture and replay the command stream which causes the issue. Capturing already exists for the most drivers. Just keep in mind that you'd need to capture all the buffers. With this, it is trivial to replay the submissions back. While replaying is simple, ideally it requires user space GPU addresses. Without kernel support for them, replaying is still doable. You just allocate a lot of memory upfront and do allocations from it. Being able to replay submissions is useful to confirm that the issue is not a fluke, but not that useful to find out the cause. What are the caveats? I think that one big caveat we didn't have to handle in Turnip are multiple queues. When we replay back the command stream, we re-upload all of the memory at each submission, which obviously doesn't work if workload is being submitted to several queues and is able to run simultaneously. Though it shouldn't matter for most cases, and a single queue could be forced. Next issue is that submission recordings with all the GPU memory could be impractically large, especially if we want to ask user to provide the one. There are also possible issues with timeline semaphores and probably something else less expected. Anyway, most of the issues happen where all of this doesn't matter. At least they did not matter in the most cases I debugged. While it's useful, it doesn't help that much on its own. The obvious next step is the ability to edit the command stream before replaying it. It is surprisingly easy to implement the editing in a minimal way. And even in this form, editing is extremely useful. Comments are emitted in a raw form, and their decoded representation is in the comments, quick and dirty. If you are going to implement it, you'd get bonus points if you could emit proper register definition without any values. You also would want to edit shaders in the command stream. Most drivers already have a way to edit GPU shader assembly in order to support the debug option to substitute the shader assembly. So it should be simple to support for command stream editing. It also may be a good idea to represent not properly decoded instructions with their raw binary form, to not alter the execution. Now that we are able to edit the command stream, how it is integrated into replay tool. The decompiler emits C code with raw commands. The compiled from it program could emit GPU command stream with any base address. The replay tool takes original command stream capture, finds unused memory range and emits edited command stream there. When replay encounters a target submission, it overrides the submitted command stream. Works like a charm. The only limitation may be self-modifying command streams. With being able to edit the command stream, the next simple but incredibly useful step is to add helpers to dump contents of GPU memory and shader registers. Printing GPU memory in command stream is easy, but the naive approach I have implemented is not perfect. If you do a memcpy equivalent in the command stream, it would require at least one cache flash, which may change the memory copied from the memory GPU would have actually seen. Probably a proper way to handle this would be to hide GPU execution from kernel and dump the memory from there. But I haven't looked too much into it. Printing shader registers is just a bit harder. It would require incrementing global offset and writing the target register at that offset. Simple while being extremely useful. You don't need a full-blown printf or GDB for shader debugging to gain their main benefits. Especially it's useful for reverse engineering the GPU, because now it's easy to see what proprietary driver is doing in its shaders. Trying to make that print interface nicer would immediately run into many issues. Want to not manually specify temporary registers? It would be much harder to allocate them at this stage. Too much trouble for a little gain. That's all features we have. So a short summary. A tool to replay command stream submissions, a tool to decompile a command stream into C code, an option to replay edited command stream, helpers to dump GPU memory from the command stream, helpers to dump shader registers. Altogether they form a powerful debug tool. Now let's move to another issue and the tool to solve it. One of the usual causes of the weird hangs and misrenderings are stale values in the GPU registers. They may appear as a random geometry flicker, or game hanging at a random moment, or a rare CTS test failure. I implemented a simple and in many cases effective way to debug it. It's not perfect, but catches more than enough issues. The solution is to write invalid values to all known registers at every possible point, and hope that if such invalid value is used, there would be a visible effect like corruption or even GPU fault. In our case, stomping registers at the start of command buffer, before each render pass and bleed, proved to be good enough. If failure is found, it's easy to bisect for the offending register. It is far from a silver bullet. There are a number of limitations one should be aware of. It could be a bit tricky if it is a combination of registers that causes the issue, and not a single register in isolation. Also, Vulkan pipelines could be set outside of render pass. though the setting of pipeline far away from the place it is used doesn't happen in real-world applications. Another limitation is that register stomping doesn't help if stale registers are between draw calls. And the final one is that default invalid value may be valid for some registers. Okay, how it looks in practice for Turnip. We mark each register with where it is used. In Turnip, we divided it into two categories. The ones used outside the render passes and bleeds, and the ones that are used inside of them. To stomp register, you need to specify the range of registers to stomp, which is necessary for bisection, and which register categories to stomp. Then you launch the application with these options and look out for any failures. We also use it in CI on a fractional CTS run. That's all of the Turnip tooling I wanted to talk about. To summarize, we have driver breadcrumbs, command stream replaying and editing, which includes GPU memory dumping and shader register dumping, and we have a debug option to find stale registers usage. Now let's talk about other tooling which helps with similar issues I talked about. As for the generic tooling, there is not much of it. There is only graphics flight recorder, which is a Vulkan layer which instruments command buffers with completion tags. It requires AMD buffer marker extension, but anyone could implement it easily. As for not so generic tooling, there is some tooling available in VKD3D Proton to help with debugging its issues. It has breadcrumbs, shader printfs, and descriptor debugging. What about Mesa itself? Most Mesa drivers have some features to somewhat assist in GPU debugging. There are many feature toggles and debug flags which help narrowing down the issues. Most drivers have a debug option to replace shaders with custom shader assembly. That is useful to debug hangs and faults in the shaders. Aside from that, there are tools to record GPU submissions and GPU crash dumps. That's all for Mesa's tooling. Now there is a really cool tool for Radeon GPU debugging on Linux called UMR. With it, one could read and write GPU registers, dump the state of all running shader waves. In case of crashes, it's possible to get an approximate location of the crash in the shader. So it seems to be a truly useful tool for debugging. There is a blog post by Meister where he uses it to debug a GPU hang in Street Fighter 6 running through VKD3D Proton. Probably the most powerful tool we may have would be a proper step-by-step shader debugger. A great job was done not so long ago by Marcel Keys to make a prototype that shows that step-by-step debugging works. This is possible because Radeon GPUs has some machinery for shader debugging. A trap could be manually set in a shader or by other means. When it is reached, a special trap handler shader is executed. This shader has additional registers available to it, and it has higher privileges than the ordinary shader. Then the communication with CPU side of the debugger is done via uncached BIOS. All of this is enough to implement step-by-step debugger for shaders. I hope this work would be upstreamed in the future. For now, you should read a lot more about it in the blog posts by Marcel Keys himself. That's all for open source solutions. Now, what about the proprietary ones? I don't know much about them, to be honest, and most of the work in the debugging space is seemingly done for compute applications and not for the graphics ones. For AMD, there is a Radeon GPU Detective. It offers a post-mortem analysis of GPU crash dumps, detailed information about page faults, and breadcrumbs. which looks similar to what Graphics Flight Recorder offers. I have not seen more advanced features there yet. Now, for NVIDIA, there is NVIDIA Insight Aftermath, which builds upon NVIDIA Insight. It makes possible to collect GPU mini-dumps, collect breadcrumbs, visualize GPU state at the moment of the crash, and show crashing shader and its registers. That's almost all what you want from shader crash debugger, aside from step-by-step debugging, of course. That's all the tools I know. So now it's time for questions. Maybe I haven't mentioned some important tool, maybe you have an idea for a new tool to implement. Ask away!
Okay, that's the time for questions now. I think he's hearing us. Danylo, do you hear us? Okay,
I'm hearing you. Yes.
Okay.
Right.
Any question?
Hi, one of the issues we've often faced with breadcrumbs on the AMD side is that when you debug games, like you don't always hang at exactly the same breadcrumb because, of course, things are dynamic. The memory dumping is a really cool feature, but I've always thought like, hey, you need to do that before the hanging command if you want to replay the hanging command. So like, in the capturing, do you have any tricks to deal with this?
So what you are saying is that if we capture the memory right after the hang, like we cannot replay it back to get the hang. Right.
So like, where do you capture it, and like, how are there any tricks to know like when you shoot?
Yes, you are right. Half right, probably, because we could capture the memory right after the hang, and rather a lot of hangs do reproduce, even if in such cases. So it's not important for all the cases, but it's something that one should keep in mind, that the memory may be not valid for replaying. That's true. Alternatively, you could capture like from the start, the memory starting from the application start, but the space requirement would be huge. Yeah, that's one of the limitations of this method.
Okay, thank you for the insight.
Any other question? Okay, that's all. Thank you so much, Danylo.
Thanks, everyone.